morning class and welcome to our lectures in sustainable energy technology. In the previous class, we discussed one of the primary modes of hydrogen production from renewable energy, that is through electrolysis from renewable electricity. And we discussed different types of electrolysis methods like cold water electrolysis, high pressure electrolysis, and high temperature steam electrolysis. So while electrolysis technology is the most developed and most commonly used technology when we are trying to generate green hydrogen, there are other methods to generate hydrogen from renewable sources as well, and we will start our discussion with those. So here I am showcasing two such methods. There are several others that we will not be discussing for brevity of time, but let us discuss two quite different methods to show how these methods can be used to generate renewable hydrogen. So the first method is photoelectrochemical cell, which is PEC. So it's a different variant of the electrolysis method, but here instead of electricity being directly fed into the electrolytic system, electricity is generated on site, in situ as we say, through a suitable photosensitive semiconductor material. So basically, sunlight is incident on a photosensitive material which generates electricity from sunlight as you do in a solar cell, and that electricity is directly being used in splitting of water into hydrogen in the same cell. So that is why it is called a photoelectrochemical cell rather than a standard electrochemical cell. So solar radiation is used to generate an electric current that in turn drives the water electrolysis. Photosensitive semiconductors like titanium oxide, strontium titanate, carbonate oxides, etc. are used as the photoelectrode. So here the term being used is a photoelectrode, which is generating electricity in its own material by when sunlight is incident on it. And this photoelectrode is kept in conjunction with an aqueous electrolyte and a counter electrode, usually made of platinum or coated with platinum, as shown in the figure. So we will discuss this figure a little bit details. And the solar to hydrogen conversion efficiencies of up to 19% have been achieved using photoelectrochemical cells. Okay. So here when we are saying conversion efficiency, we are meaning is what fraction of the solar energy has been converted into the chemical energy of hydrogen that is being generated. Okay. Or what fraction of the solar energy can be used to split water into hydrogen. So either way. Okay, so around 19%, which is not very bad if you consider that usual efficiencies of a PV cell that generates electricity from solar is around 21% at most. But these are still not commercial grade systems. We have prototypes and certain prototype systems that have been developed, but this is not yet at a technologically mature state. So now if we look at the figure a little bit more detail. So here is your photoelectrochemical cell made of usually titanium oxide or other such materials. Basically this material is a multi-gap semiconductor made of p-n junctions, but silicon is not used in this case for certain reasons that we will not go into. Titanium oxide, carbonate salts, these are the type of carbonate oxides, these are used primarily in these cases because it is doing two things. It is generating the electricity and it is used and the material itself is being used to help in the breakdown of water into hydrogen atoms and electrons. So it has to do a dual function, correct? So that is why the material choice is different. A different type of a semiconductor, photovoltaic semiconductor is used. Okay. So photons are entering through this transparent glass panel and the electricity, the electrons are generated in the semiconductor p-n junction semiconductor by the incident photons, as we discussed for the solar PV cells, and this electron, the energy is used to break water into H plus and E minus. Okay, so the electrons are moving outwards and water is being breaking into protons and electrons and oxygen, okay, in this cell itself, in this electrode itself. Then the H plus ions are moving through the aqueous electrolyte made of sodium sulfate for this design. So an aqueous electrolyte, sodium sulfate electrolyte, sodium sulfate salt which is dissolved in water is used as the electrolyte, and the photon flux H plus is moving from the anode here towards the cathode, and at the cathode the H plus ions coming through the electrolyte and the electrons coming from the external circuit are coming together to produce hydrogen, okay, and this hydrogen is being taken out here, all right, and the oxygen is being taken out here, all right, and the water basically is absorbed from this aqueous electrolyte. So there has to be a flow of water into this electrolyte system, okay. So that is how this photoelectrochemical cell works. It converts solar energy into electrical energy, and the electrical energy is used to break water, and the electrons are going into the external circuit and transferred to the cathode, and there it is recombining with the H plus ions to produce hydrogen. The second type of hydrogen production method is using heat energy and chemical processes to generate hydrogen. Okay, so these are called thermochemical and hybrid thermochemical water splitting. It's thermochemical because it is using a combination of thermal energy and chemical reactions to generate hydrogen, and if it's hybrid, it uses thermal energy and electrical energy and chemical reactions all together for splitting of water to generate hydrogen. Okay. So these involve a series of chemical reactions that occur in a loop, usually at high temperatures with the final effect of water decomposition. Okay. So a series of reactions are occurring in a loop using certain intermediate chemicals, and the final impact of this entire chemical loop is splitting of water into hydrogen and oxygen. And usually these chemical reactions are driven by heat, but parts of the loop may also be electrolytic in nature, which is using electrical energy. The intermediate chemicals are recovered at the end of the chemical cycle. The system is called a hybrid system if some of the reactions occur through electrolysis and require electricity, as we discussed. Typical temperatures required depend on the cycle being used and range from 600 kelvins to 1200 kelvins. So approximately 300 degrees centigrade to around 900 degrees centigrade. Okay, and this thermal energy and the high temperatures can be sourced from either concentrated solar power, nuclear power, or biomass combustion systems. So nuclear power can generate a lot of thermal energy, concentrated solar can generate a lot of thermal energy, biomass systems can generate a lot of thermal energy. These systems can deliver the heat required to drive this thermochemical and hybrid thermochemical water splitting reactions. Usually geothermal systems will not be able to deliver this heat because the temperatures are 300 degrees centigrades and above, which is hard to find in a geothermal system. Okay, so let us look at two examples. One is this purely thermal sulfur iodine cycle, and this is hybrid sulfur thermochemical cycle. So we will look at both of these once in turn. So this is the chemical loop. First we will look at the central reaction where water is coming, and this temperature is relatively low, less than 120 degrees. It has to be high, but it is to be around 100 to 120 degrees maximum. So here iodine and sulfur dioxide is reacting with water, maybe water vapor primarily, to form basically steam at around 100 to 120 degrees centigrade to produce hydrogen iodide and sulfuric acid. Okay, so iodine, sulfur dioxide and vaporized water are reacting with each other to produce hydrogen iodide and sulfuric acid at temperatures less than 120 degrees centigrade. Okay, now this hydrogen iodide is fed into a second chemical reactor, let's say, which is operating at temperatures above 300 degrees centigrade, so significantly higher temperatures now, and there this hydrogen iodide breaks down into iodine and hydrogen. So this is basically the cracking of hydrogen iodide back into iodine and hydrogen, and this hydrogen is then extracted and this iodine is fed back into the first reactor here, where it is again being reused. Okay, so what is happening? Iodine, sulfur dioxide, water vapor reacting with each other to produce hydrogen iodide and sulfuric acid. The hydrogen iodide breaking down at higher temperature in a separate reactor to produce iodine and hydrogen. Hydrogen getting extracted and iodine coming back into the system. Fine. What happens to the sulfur dioxide, sulfuric acid? This sulfuric acid is fed into the highest temperature reactor, which is operating at 800 degrees centigrade and above, where it is breaking down into sulfur dioxide, water vapor and oxygen. Alright, and this water vapor is fed back, this sulfur dioxide and water vapor is fed back into the system. Note that here you have 2 moles of water and here you have 1 mole of water. So 1 mole of water is being consumed, so you have to add water from the external system, obviously because you are generating hydrogen. And this is the region where you need to generate a lot of heat, so you add a heat from a high temperature source. Okay, and the temperatures are above 800 degrees centigrade here to break down sulfuric acid, which is significant. Okay, and the oxygen is being recovered here. Now let us look at the hybrid thermochemical cycle, which usually requires which has lesser number of steps. Okay. So in this hybrid thermochemical cycle, we have the sulfur dioxide again at 800 degrees centigrade breaking down into sulfuric acid, thermal decomposition of sulfuric acid into sulfur dioxide, water vapor and oxygen. We are taking out this oxygen and feeding the sulfur dioxide and water vapor into the electrolytic cell, where you are using electricity to drive this reaction here, where water and sulfur dioxide are reacting with each other to produce sulfuric acid and hydrogen. So there will be 2 half cells. One half cell will be generating the hydrogen from water vapor by splitting water vapor and producing hydrogen. In the other reaction, electrons will be used to, and the sulfur dioxide will be converted to H2SO4. Okay. And here the electrolytic cell usually works at 100 degrees centigrade. So the water is coming in and steam form. Alright. So this is a high temperature electrolytic cell and this is high temperature thermal decomposition. Alright. So these methods so there are certain advantages and disadvantages of these methods. The first advantage is you can use thermal energy. Okay, so often there is a loss associated with converting thermal energy into electrical energy. So for example, in a concentrated solar power system, instead of using concentrated solar energy to generate electricity, you can use this type of a system to use the temperature of the molten salts, which can be stored at 800 degrees centigrade and above, to generate hydrogen. And this hydrogen then can become your energy material that this concentrated solar power plant is generating. And similarly, if you have a biomass combustion system, instead of generating electricity, you can use this process to generate hydrogen instead. Okay, so that is one advantage. One disadvantage is there are fewer sources of renewable thermal energy compared to renewable electrical energy. So there that problem comes. Okay, that this type of hydrogen production systems will not pair well with solar PV or wind electricity, etc. Okay. So this kind of gives us a snapshot of hydrogen production. There are several other types of hydrogen production like biomass gasification to produce syngas, then you can convert that syngas through what is called a water gas shift reaction to produce more hydrogen and carbon dioxide. That is also a renewable way as long as the biomass is sourced renewably. There are other biological methods where you are using certain types of microbes in the presence of sunlight to generate hydrogen directly through water splitting. So water splitting, biochemical water splitting systems as we discussed earlier. So for example, many of these biophotolysis systems can be used like that. We are not going into a lot of details there. I am just giving you some of the highlights of common ways of hydrogen production as of now. Now that we have produced hydrogen, the next question is how do we store hydrogen? Okay, there are certain advantages of hydrogen and certain disadvantages. One major disadvantage is hydrogen is hard to store because it is an extremely light gas. Okay, so hydrogen is the lightest element in the universe and has high specific energy. So it's one of the lightest materials. Basically, it's 1 mole is 2 kgs, correct? 1 kilomole is 2 kgs. It's the lightest element in the universe. So it has very low density but very high specific energy density. Okay, so its volumetric density is low, but its specific energy, this energy per unit mass, is very high. Okay, so it has a high specific energy density of 120 megajoules per kg. So if you can store 1 kg of hydrogen, you can get 120 megajoules of energy out of that 1 kg. Okay, compared to liquid hydrocarbons like gasoline, which is around 43 megajoules per kg. So more than 3 times the energy content per unit mass hydrogen has compared to hydrocarbons like gas, basically petrol, for example. Okay, so 320 grams of hydrogen has the same energy content as around 1 kg of gasoline. So that's the kind of the comparison you can make. That is an advantage, high energy density per unit mass, but it has very low energy density per unit volume. Okay, it's a very light gas. Volume occupied by 1 kg of gasoline is 1.3 liters. Okay, so its density is slightly lower than water. Okay, 1 kg of water usually is 1 liters, right? But 324 grams of hydrogen at standard temperature and pressure occupies 3932 liters. Okay, so this is the 324 grams of hydrogen is the same energy density as energy content as 1 kg of gasoline. So this is good, but that 324 grams will occupy 3932 liters of volume at standard temperature and pressure. So if temperature is around 298 kelvins, pressure is around 1 atmosphere, then this is the volume this gas will occupy. All right. So its volumetric energy density at STP is extremely low compared to gasoline. Okay. Hence, hydrogen requires to be compressed or liquefied for usage in energy infrastructure so that you can get the volumetric energy density up and you can get manageable volumes within a certain limited space. Okay, so that's the challenge. Now, how can this be done? It can be stored as a compressed gas at standard temperatures and very high pressures, 400 to 700 bars. So 400 times atmospheric pressure to 700 times the atmospheric pressure. So you compress the gas at two very high pressures and store hydrogen as a compressed gas at 400 bars to 700 bars containers or cylinders. Okay. That is one option. The second option is you convert hydrogen into liquid at very low temperatures. So this is called a cryogenic liquid. Liquefied hydrogen, the hydrogen liquefies at extremely low temperatures, around 20 kelvins at 1 atmosphere pressure. So if the pressure is 1 atmosphere, then hydrogen will become a liquid at around 20 kelvins. So 20 kelvins, you understand, just 20 degrees above absolute zero. Okay, so it is basically around minus 253 degrees centigrade. So it's extremely low temperatures. Okay, so there is a challenge associated with creating such cryogenic conditions. Liquid hydrogen has been generated and is often used in rocketry systems. Okay, where cryogenic hydrogen is used as a fuel. But it is expensive, as we will see, and it is used in some places, but not commercially used at a wide scale because of the costs associated. It can also be stored as physical binding of hydrogen molecule in a solid material matrix. So suppose you have a porous solid and the hydrogen gas diffuses into that solid and starts being adsorbed or binding with the solid particles. This is physical binding, and hydrogen gets adsorbed into the metal matrix and gets stored that way. Okay. So that is another way of storing hydrogen. Another option is chemical bonding, to synthesize a denser molecule that can later release hydrogen. So for example, you can create ammonia out of hydrogen, NH3, and ammonia is a far denser molecule and far easier to store, and when you need to extract hydrogen, you heat up ammonia and it will break down back into nitrogen and hydrogen. Okay. So that is another way of storing hydrogen in terms of chemical bonds. So the volumetric energy density of hydrogen compared to gasoline can be looked at. Okay. So this is the specific energy density, megajoules per kg, or 120 to 43. Okay. Now gasoline's volumetric energy density is 32,317 megajoules per meter cube. Okay. So 1 meter cube of gasoline by volume will store 32.3 megajoules of energy, quite a lot of energy. Compare this with hydrogen's volumetric energy density, which is just 10.8 megajoules per meter cube at STP. Okay. So you can see that the hydrogen's energy density at STP is more than 3000 times lower than that of gasoline. But this can increase if you do certain things to hydrogen. So if you compress it to 400 bars, that energy density goes to 31,000 megajoules per meter cube. If you go up to 700 bars and compress it, the energy density goes to 48,000 megajoules per meter cube. Still significantly small, but now it's around 6 to 7 times. Okay. So between 6 and 7 times lower than the energy density of gasoline. Okay. And finally, if you go as to a cryogenic liquid at 20 kelvins, it will go to 8,500 megajoules per kg. So around 4 times lower, somewhat less than 4 times lower than that of gasoline. Okay. So from 10 megajoules per meter cube to 3,100, 4,800 and 8,500 megajoules per meter cube. Okay. Now these are all lower energy densities than standard hydrocarbons. But if you think of hydrogen as an energy storage material, any of these values are significantly greater than the energy densities associated with other energy storage materials we have still discussed, like batteries, supercapacitors and all of those, like hydroelectric power plants, right? You can look at the energy density of a reservoir of water, maybe 500 meters above the lower riverbed, and see what is the energy density per meter cube of that water, just the gravitational potential energy. Okay, it will be much lower. Similarly for batteries, supercapacitors, etc. Okay, so hydrogen, even though it's significantly lower compared to gasoline under compressed or liquefied forms, is still higher than many other energy storage materials that are available in the market, making it an attractive choice for many energy storage related applications. So I will stop here today. In the next class, we will discuss a little bit of detail of how these types of storages can be done, like how you can do compression, how you can do cryogenic liquefaction, how you can do physical or chemical bonding. Okay. So thank you for listening and see you in the next class. Thank you.